Welcome to the castle. In medieval times, a squire was the first step toward becoming a knight. They were eager, brave, but let's be honest, mostly just running around, polishing armor, opening gates for everyone. That's a bit like where many of us start with Kubernetes security, eager to protect our clusters, but we don't know much or we don't have the proper tools. I'm Donia Chaiehloudj, and today I'm your guide, your security guide today on this journey through moats, gates, and policies, all within the mysterious kingdom of Kubernetes. By the end of this session, you'll live not just as a squire, but as a network knight, someone who understands how to defend the cluster the cloud-native way. So grab your sword or your YAML file, more YAML file, sadly, and let's get started. Imagine a castle with no guards, no gates, no rule. Everyone can enter, merchants, travelers, maybe dragons, even auditors. That's what a Kubernetes cluster looks like with our network policy when you deploy it as is. Every pod can talk to any pod, every service is exposed to the world. So we'll start here with a wide open cluster and gradually harden it step by step until we reach the full knighthood. In the old world, firewalls were the castle walls. They worked when the world was static, fixed IPs with cables. You had to define manually what you wanted to say on one data center, one big gate. You'd say hello TCP, 443, whatever IP, and life was good. It was before. But Kubernetes isn't a static castle. It's a moving one. Pods appear, disappear, move between nodes. IPs are assigned to one pod and can be reassigned to another one and change faster than you can blink. Building firewalls, for that, it's like trying to guard a flock of teleporting sheep. And the biggest problem, firewalls only see where traffic comes from, not who is sending it or why. And that's the mindset that we'll break down today. The shift from the walls to identity. So you reach the level of the squire. He's new to the castle, he's eager, curious, and just got access to his very first Kubernetes cluster. There are no guards again, no walls, no rules. The gates are wide open, and everyone can talk to everyone. The cook maybe can shout across the courtyard to the queen's chamber, whatever. Some gossip. It's lively, but it's chaos. That's what we're going to fix. You need to organize your Kubernetes cluster. And to do so, you have to do some steps before routing any traffic. First, you have to think class of workloads. Today, in this current world, we have AI workloads. We have the traditional front-end, back-end, UI, databases, all these kind of workloads that you're going to separate. And most of the time, you separate resources logically per namespace, like space of rooms in a castle. And you also have to label your resources thoughtfully, because we're going to need these labels for the identity mindset right after. So a network policy has three main parts. The first one is the royal decree. The kind network policy with its metadata, it's the law itself. Then we have a second part where this is the assignment. We have the pod selector and policy types, who this law applies to, and whether it governs ingress or egress. And finally, we have the guest list. So the rules that are under egress or egress, who may enter or not, from where, and through which ports. It's like declaring that this law applies to the kitchen, only the cook may enter, the door is 80/80. And that's the Kubernetes of as medieval bureaucracy. In the real world, it looks like this. We have the front end and the back end, and probably an external app that wants to access our cluster. And you will write this network policy explaining that on the pod selector, I want only the back end to be accessed by the front end, and not everyone from outside of our castle. We'll break down a bit later. You reach the level 1. We install guards at every gate, the L4. Pods now obey rules. Front-end can talk to back-end, but not other way around. You can see access as a privilege, not a default. But our guards are still limited. They can check who enters, but they can't read the ladders being carried. And for that, we need something smarter. This is where the network policies plugin enter. They can go beyond what we already have on a default Kubernetes cluster and the Kubernetes Network Policy API. There are many of them on the market. There are 3 categories, like the core CNIs. You can think of them as the knights that everyone knows. They handle the basics like connecting pods, routing packets, enforcing policies. In the middle, we have the bridge builders, the Multus and Canal mostly, we'll see. They let you mix and match multiple CNI or combine network with policies. It's very useful when you want to do, for example, migration from one plugin to another, so you can have both at the same time and have no downtime. And in the clouds, there are the role envoys at Azure, GCP, whatever, who connect Kubernetes directly to their own VPCs. And finally, a few wise elders like WeaveNet. They're simple, self-heating from the old time, still doing the job. So while each kingdom has its own style of roads, the goal is the same: connect and route the pods safely and efficiently. And today, our story focuses on one night in particular. It's Cilium, the eBPF port 1. But all I'm saying can be applied to any of them, mostly. So let's enter the network night, Cilium. Instead of building walls, Cilium watches the fabric of the kingdom itself, the Linux kernel. It uses the technology eBPF to see, decide, and act directly inside the kernel without overhead. Mostly without overhead. The knight doesn't just guard gates, they understand intent, which service is speaking, which API is being called, even which DNS name is resolved. This is where Kubernetes security becomes smart. And we can see the difference between Kubernetes network policy, the default one, and the one here from Cilium, the Cilium network policy. It's a specific CRD, a custom resource definition. And we can see that on the Kubernetes side, we operate mainly at layer 3 and 4, the network and the transport layers. They control which pods can connect to which pod and which ports are protocols. But they don't inspect the traffic content, as mentioned. Cilium extends this model beyond L3, L4 by introducing application layer awareness. So using eBPF, you can observe and enforce policy at layer 7, the application layer, and it understands whether the traffic is HTTP request, gRPC, DNS lookup, name it. It can allow or deny egress to certain domains. So you can think as being more granular. It enforces service identity based on labels and not IPs. Again, we are talking here about identities. And what are identities? So in the Ottoman courts, people were recognized by where they came from, but by who they were. So everyone carried a seal, a mark of identity, showing their role and purpose. It didn't matter if they entered through one gate or another. What mattered was that the seal was trusted. That's exactly how Cilium handles identity in Kubernetes. Pods are born, replaced, rescheduled, and today's front end might have a completely different IP tomorrow. So instead of chasing those changes, Cilium assigns each workload a stable identity based on its set of labels. That's why I said at the beginning that labeling thoughtfully your workloads is very important here, because you want to apply network policies to resources with a set of labels that make sense. So here we have the role front end, we have the back end, and in the Linux kernel, what Cilium and eBPF will store is a map with the set of labels and a unique identity representing your endpoint, your pod. So no matter what is the IP at the end, we can route the traffic. Definitely more smarter. So let's see one example in action. So I have my assistant that can talk to the queen, and I have an invader that wants to come into my castle. Currently, all the doors are wide open because I just opened my castle, my cluster. Then I want to apply a first rule, which is a deny all. So I'm going to say I don't want any traffic to go between anyone. And you can say, the assistant is panicking, how and why can't I reach the queen? Yeah, that's perfect. Actually, this is where I want to start with. Now we're going to select which door we want to open using precise rules. So here is the concrete example between front-end and back-end pods and the network policy that is applied. And what you can see is that the endpoint selector is empty because it applies to anyone, all the endpoint selector, all the pods. And I'm saying ingress here. I could add egress, but let's say ingress at the moment. Now I want to say that only the assistant can talk to the queen. Because the castle is still tight, no one can talk to anyone. That's not good. We want to be able to open that. And how do we open this flow? Is by allowing the front end to talk to the back end and saying, instead of denying all, I'm going to select the back end endpoints and apply an ingress. All the traffic coming from the endpoints that are labeled front end can access it and can communicate with it. And by default, it will deny all the rest. That means that only the front end pod here can talk to backend and not an invader from an external app. We've seen the equivalent to the Kubernetes network policy because it was pod to pod. Now I want to go deeper with the L4 filtering, which is also possible, but yeah. With Kubernetes network policy, sorry. So I'm going to say that, again, the backend and the front end can communicate, but with a specific port and a specific protocol. It means that if I want to communicate with UDP instead of TCP, it's not going to work. So you are filtering more granularly again. Let's move on to the L7, which is, I think, the most interesting one. So you can filter on HTTP. Here I have my assistant talking to the queen. And I want to say that the assistant can retrieve letters, the correspondent from my queen. She can also give her some letters and her correspondence to read. But she cannot get the queen to go somewhere. Like the queen can decide for herself. You see? So our policy no longer say that the assistant may talk to the queen. We'll see how it translates between front end and back end. So again, we're going to say that we have the front end pod. They can actually egress to back end with a specific port and a specific protocol, and then specify the method and the path that are allowed. So you can think in the real world as microservices communicate together, the front end and the back end, and you can allow only specific endpoints to be accessible. Especially in the microservices world, we are separating domains and like functionality, so that's kind of interesting in that case. I reverted the network policy here. I'm not sure if you can see it, but I just say that from the endpoint front end and the back end, I've just reversed the egress and the ingress. So it's just to show you that you can think about the traffic going from one resource to another, or what traffic is coming into the current pod. Mostly, you will think about egress because I think it's more natural in our mind. But sometimes it can be interesting, especially if you're thinking about a broader scope of a cluster, like a namespace, what's ingressing. You can filter also per DNS. And it means that here my queen can talk to her messenger or her assistant and fetch for the address of her doctor. Where can I find betterhelp.com, for example? And here, the external DNS will get back to the messenger and then the queen and give the doctor address. Can you guess what is the role messenger in the real world? Anyone want to try? Let me give the solution in that case. Oh, just then she fetched the doctors. It's the kubedns doctor, the kubedns pod, sorry. So the backend pod can communicate with the kubedns asking for a resolution of a DNS address in a cluster. kubedns comes as default on a cluster, but you will have to deploy a CNI to have actually this layer. What is interesting here is that, so on the network policy side, you can see at the top what we've seen before, the metadata. And then I want to say that all the endpoints that are labeled backend can communicate with kubedns, because I have to authorize this traffic first to say that I want to resolve actually one address. And then the kubedns will access the external DNS and ask for betterhelp.com and get back with the IP address. And because on the network policy, we say at the end that you can do DNS resolution and actually access it on betterhelp.com, precising the DNS address, the backend pod can directly fetch the betterhelp.com website. So she can access her doctor. Finally, what I want to mention here is that we talk about Cilium network policy in specific namespaces. But when you are doing platform engineering or security engineering, like having real distributed system, you will think about it very large, at a very large scale, deploying thousands of resources on, I don't know, thousands of nodes. So you'll have to think about what you can apply on cluster-wide network policy, which traffic you're going to allow, or what can egress, and then you can override on specific namespaces, for example, for databases or front-end and back-end, because you are thinking about how you organize your resources logically per namespaces. So that's the mindset and the intent behind security and network policies. This is what it looks like in Cilium world, with the Cilium cluster-wide network policy, which is another specific CRD, and then per namespace, the network policy that you're going to apply on all the pods on one namespace. So it sets your overall strategy, the outer walls of the kingdom. The CNP refine the details, the guards endure inside each keep. And together, they form a layered defense model. So you start broad to protect everyone, then narrow down to enforce the right behavior locally. That's how you scale the security without chaos, most of the time. So I'm happy to tell you that you're now a network knight, that you're fully trained defender, using your intelligence, your knowledge to keep the kingdom safe. We've seen the layer 3, 4, layer 7, the DNS, FQDN. You have all the basic stuff, a little bit of the cluster-wide, just a touch. And the network knight isn't just reacting. They're anticipating, enforcing, learning. Network policies are iteration. You have to audit and verify them all the time. And by reaching this level, you're going to, from open castle, the chaos, to a kingdom where every pod, every packet, every API call has meaning and protection. This is the essence of defending the Kubernetes castle the cloud-native way. And this is all the tenets of the network knight, some principle to remember. This is only for the record, I would say. So thou shalt protect every pod in the realm. Thou shalt precise in their rules. Thou shalt deny by default and grant by grace. Thou shalt keep watch and update thy defenses. Thou shalt take the defenses with time on hand. You have all the translation just below. Thank you very much. You have all the resources and credits. I would recommend to have a look to the book that is mentioned here. There are also blog posted. I wanted to thank you a lot, my colleagues, for the resources that I've been basing my talk on. Feedback is a gift, so if you want just to say thank you, hi, it was a mess, you can. I'm happy to improve myself. And I'm also part of the Merge Forward initiative. I don't know if you heard about it. So this is the umbrella behind all the DI chapters from the CNCF and the Cloud Native Foundation. I would recommend joining if you're interested to contribute or just have a look. There's a party tonight also. So thank you very much. Have a good day.
Thank you.